Good. Okay, so today we're going to start our investigation of the memory systems, which basically comes down to caches. And you took my undergrad, you took caching. Jordan, did you do caches in undergrad?
No, we did not.
No, we did not. All right, well, so we're going to go through a lot of information today about caching. Most of this should have been covered from undergrad. Maybe some, not quite all of it wasn't, don't feel too bad, but yeah, we're going to run through it, and then next time we're going to start talking about more advanced topics in caching, with, namely with multi-core systems. Okay, so in undergrad, you should have discussed two structures for holding data. Hopefully you've talked about a register file, which is what's used in the processor. You've done this in your in-order pipeline. And then you have memory, which is a bigger array. You did this as well in your simulator. Several methods to implement this. You do static storage made with logic gates. Hopefully you did have some digital circuits class. If not, excuse me. You need help? Or you could do ROMs and other things with diodes. So, wow. Let me skip these for a second and go right over to this picture. So cache design. It's good to think of it as the memory pyramid, where maybe at the bottom you have your disk, which usually has many gigabytes. Okay, that should be terabytes nowadays. Many terabytes of information. Your memory, okay, nowadays probably a few gigabytes is usually what you have. Then you might start having your cache, 32 megs. I think I've started seeing them up to 64 or 128 as well. Your L1 cache, which is usually definitely in the kilobyte range of size-wise. And then, of course, you have your register file, which might be hundreds of bytes. You have 32-bit registers. In our system, there's 8 of those, so 8 times 32 is whatever, 200, was it 256? Yeah, 256 bytes. All right, so which of these are fast and which of these are slow?
The top to the bottom, fast to slow.
Fast to slow. So, as with architecture, slow is fast, big is slow. So something that's very small is going to be very quick to access, while trying to go to disk is going to take a very long time to access it. Let me see if I give you the good analogy. So yeah, register is usually 1 cycle access. L1, 1 to 3 cycles. Of course, they've been messing around with the cycle time. Sometimes you get up to about 7 cycles to access your L1. Your L2 might be 15. Yeah, I've seen them going about 10 to 20 cycles. Memories, yeah, usually about 50 to 300. That's been staying pretty constant. And these are clock cycles in your processor. Now, hold on, what does this mean? That means when you do a load, like if you need to read something from register, you have 1 cycle access. Okay, that's what you want. But if you're trying to do a load word, if it's in your L1 cache, you would take 1 to 3 cycles, L2 6 to 15, and then your main memory 300. And then your disk, well, yeah, millions of cycles. Literally, if your program is on disk, it takes your processor millions of cycles just to read something from the disk, load it into memory, and then give it to you. Okay, so I gleaned over why we're doing this. I forgot to mention that. But if you think about this, if you didn't have the caches here, and you just had our in-order pipeline where you had your registers and your memory, every time you tried to do a load word, let's say it took 300 cycles, which means that your processor would literally stall for 300 cycles inside your in-order pipeline. It would just sit there with no ops for 300 cycles. Not an efficient solution. Hopefully you can see that. But if you keep smaller amounts of memory that have shorter access time, with the hopes that it's in those pieces of memory, maybe it can only take 1 to 3 cycles, or maybe if it's a little bigger piece of data, it would take 6 to 15 cycles to access, and then you'd have fewer no-ops going through your pipeline. So do you understand why a cache is important, at least? It's basically a smaller memory to help you access quickly, things more quickly. So you have this hierarchy. Well, nowadays there's also an L3 cache between the L2 and the memory as well, which is usually if I recall, it's more like 30 to maybe 50-ish cycles. So that's going on in there.
What is the difference between the L1, L2?
Size. So you have your processor, it first checks the L1. Since it's smaller than the L2, the L1 is going to be faster. So you want it to be in the L1.
So that's just layer 1, layer 2, is that what it
Yeah, layer 1, layer 2, or level 1, layer 2. They also have level 3 cache as well. This is just to take advantage. The idea is that if you're in a tight loop, you can do most of your calculations in your L1 cache. If you're going beyond the L1 cache, kind of jumping around, maybe they can take advantage of I guess, larger data structures and still keep the cycle time down. Because if it doesn't fit your L1 cache, you're usually just going to main memory anyways, and that's not good. So that's why L2 is there to capture a couple more things. The L3 is kind of a continuation of that, but nowadays the L3 is really used as the shared part. And we'll get into that when we talk about multi-core, because the idea is that most cores have their own L1 and L2 cache that's personal to the core. But if you're doing any communication between cores, it's good to have a cache, kind of like a system cache, so to speak. So all your cores share a single unified L3 cache, which again, smaller than 8 gigs of memory. Maybe it's 128 megs. Yeah, definitely bigger than your L2, but it's there to share and at least speed up processes. The idea, of course, here is that hopefully most of your program memory calculations can be put inside of the L1 cache, so that your loads are only 1 to 3 cycles as opposed to 300. And then hopefully you never have to write to disk, because yeah, it just takes forever. Okay. Ooh, historical cost of memories. As you can see, keep in mind that this is a logarithmic scale, so it's not just a linear decrease, it is an exponential decrease in price per, what was it? It should be price per megabyte. Okay. 0.0001 cents. So solid state drives are getting pretty cheap. What we got? Flash sticks. What's the green one? DIMMs. That's your what RAMs we use right now. Flip flops. I don't even see flip flops up there. Oh, good old floppy drives. There they are.
Oh, they disappeared.
And then what happened to floppy drives? So yeah, 1950, really expensive to have 1 million of these.
What's the flip-flop?
So a flip-flop is basically 1-bit register. So it uses it uses latches and uses a D latch and an SR latch in order to implement memory that can be clocked. So it only changes after the clock. It's an old. Your register file uses flip-flops. So your register file is still flip-flop based, but other RAMs are cheaper, but they have slower access time. So, and big drives. Actually, don't know what that is. I'm just assuming it's like a giant cylinder or something. Matt, sounds good?
Yep.
Sounds great.
The tape's actually trash bags.
Yeah. Good. Okay. So the historical cost. We need to figure out how we can build out our cache. There's many different things we are going to need to address over here. Let me at least talk about that. Like I said, we are hoping that most of our program fits in the L1 cache. We're going to have to discuss how we can achieve that, and there's different techniques to take advantage of what's called temporal locality or spatial locality. We'll talk about how do we address keeping what we need in the cache and keep it there. And then there's the other problem is, of course, how are we going to build these caches? What's the best thing to use? So, option 1, you could build your memory out of SRAM, about 5 to 10 nanoseconds access, which is all right. Which is pretty fast. Decoders are big, arrays are big, costs a lot of money. This was true as about 2 or 3 years ago. SRAM is about $7 per megabyte. So it'd be about 43 cents for our design, because remember we only use 64 words. So we don't use quite a megabyte. So 43 cents for our design, that's not bad. 28,672 for MIPS, that's not good. And then, yeah, x86 would be 123 trillion. And that's to give all in the 64-bit memory space. So yeah, probably not a good solution for large memories. We could build it out of DRAM, save a bit in a capacitor. And it takes about 100 nanoseconds to access, but the other problem with the way DRAM works is that it has to be refreshed. Otherwise, because it's based on kind of capacitance, and eventually it'll lose its memory, so it has to stall for a couple cycles to refresh itself. But the real problem is it takes 100 nanoseconds to access, which means after a point you're going to build a fast processor, and then you will be stalling anyways because it takes too long to access RAM. Right, Matt?
Right.
$68 per gigabyte, so that is cheaper. Actually, it's a lot cheaper nowadays. How much is it? How much is DRAM for 8 gigs? Is it about $60?
Sure.
Sure. Okay. So we can divide these numbers by 8. So less than a penny for our design. That sounds great. 272 for MIPS. Not great, but definitely something buyers will pay for. And $1 trillion for our latest 64-bit, which is not going to happen unless the government decides to buy this for whatever reason. Now we could use it for doing disks. Access is about, what is that, 10 million nanoseconds? So 0.01 seconds in order to access something. Not good. Yeah, we could have stopped, aka your processor takes so long to load. By the time, you might as well have an old processor from the 70s to get everything working, because it doesn't matter, it takes too long to load. 25 cents per gigabyte. How cheap are hard drives nowadays? How much is it per terabyte?
60 bucks. Not SSD though. Actually, like 60 bucks.
60 bucks for a terabyte? Yeah, so wow, it's even cheaper than 25 cents per gigabyte. Yeah, for our design, basically nothing. $1 for MIPS. Still going to be, probably not 4 billion, maybe closer to 500 million for x86. So still not the best solution for x86. But for our design, still be good. And the other problem is this is way too slow. So we want a memory system that runs at a clock speed about 1 nanosecond. If you have a gigahertz, you do the math, your clock rate is 1 nanosecond. We want memory systems that we can afford, so maybe 25 to 30% of the total cost. As I just showed you, options 1 through 3 are too slow. And options 1, or actually all of them, are too expensive, so we have to come up with something else. The idea is you use a little bit of everything wisely. So your small memory, aka your L1 cache, will probably be of SRAM. It's fast, and it means it's also cheap because we don't want a lot of it. And then maybe a larger amount for DRAM and hope you rarely have to use it. And then for a really big amount, you'll use disk storage. And these are just getting cheaper. Also, we don't want to buy 2 to 64 bytes of anyways. Yeah, there'd be no point to it. And good luck formatting that.
You just buy it pre-formatted.
I see how it is. So the idea is we'll use a small array for SRAM, the cache, use a larger amount for DRAM for main memory, and then disks for virtual memory. We'll talk a little bit about virtual memory for a while. Don't try and buy 2 to 64 bytes of anything. We have no need, at least not yet. So here's again the memory hierarchy. Your cache is usually fast, or low cost, fast access, small cost. You can only access too much. And then latency is slower down here, but faster up here. Okay. We've alluded to what architectural and non-architectural means. Architecture is what the machine language sees. Okay, when you're writing assembly code, and hopefully you all did assembly in undergrad. Did you all do assembly? Okay, great. So assembly is the architecture view of what it provides. You're going to have this many registers. You can access it with these instructions. That's the architectural view. How it's implemented in the background is the non-architectural view because it's part of your actual architecture of the processor. So if you have a cache or main memory, that's non-architectural because you don't do anything with the cache inside of assembly. Well, there's a couple instructions nowadays to flush the cache, but in general, it's not considered architectural. The machine language doesn't know about it, doesn't need to. And the other important part is if you make a non-architectural change, you don't have to break up, may not break it up into small pieces, or break it up at all. The other nice thing is you maintain backwards compatibility. Okay. So we want to, with our cache, we want to be able to hold data we think is most likely to be referenced. We want to maximize the number of references that are serviced. Yep. How do we decide the most likely access locations are? So does anyone remember what we do about this?
Randomly pick one.
Randomly pick one. All right, terrible idea. Good try.
The lowest memory locations, I mean,
Okay.
yes.
Let me let that think for a while. We'll get to that.
I'd hate to spoil it.
You hate to spoil it? I know. All right. Analogy that I've run across that I think works very well is think of it if you're hungry, right? And option one, which is kind of like going to the L1 cache, is you're hungry, there's no food right in front of you, so you have to go to the refrigerator. All right, it may take a minute, latency a minute in order to do it. Two, it's not in the refrigerator. Oh, you're gonna have to go to the store, buy it, come back. Maybe 20 or 30 minutes, unless of course there's traffic, then it'll be an hour. But you can still get it done within a day. That's kind of like your L2 cache. Or main memory, somewhere in here. Option three is you buy seeds and you plant it, you grow it, you wait, and then you can harvest. This
Sounds
one's
sustainable.
sounds sustainable. So this is about 6 months. That's like your disk drive. So whenever you have to go to disk, that's like if you have to grow your own food. It's about the best analogy I've come across. Don't ever go to disk. It's terrible. Okay. Here's a good question. I'll let y'all answer. Let's say you have a cache that takes 1 cycle access time, main memory takes 100, and disk takes only 10,000. That's a pretty fast disk. What's the average access time for 100 memory references if you measure 90% of the cache accesses are hits, 80% of the accesses to memory are hits? So think about it. So what that means is
Wasn't that in the homework?
probably.
I think it was.
So what does that mean, guys? Matt.
I mean, some stuff.
So you have 100%, right, of something. 90% of that 100% takes how long?
Wait, say that again?
1 cycle.
Yeah. So 90% takes 1 cycle, so 0.9 times 1 cycle. All right. So 90% takes 1 cycle. We're trying to figure out how long the average memory latency takes. What's the average? All right, so next are hits, and 80% of accesses to main memory are hits. So what are we doing here? What's left over if you take 90%?
10%.
10. So then what's 80% of 10%?
80%. Oh, that's what you're saying. 80% of 10% is going to be 0.08.
Yeah, 0.08. So we got AKA 8%. And how long does that one take?
That's going to be 100.
100. All right, and then what's left over?
That's it.
Well, 0.9 plus 0.08 is 0.98. That's not 100%. So we're still missing 2%. That last 2% is doing what? Or
It's
is-
going to disk.
Yeah, it has to go to disk, which takes 10,000. All right, someone do the math.
Nope.
Arithmetic, I mean. This is actually not math, this is arithmetic. Anyone?
1.48.
Nope.
The wording did trick me for a second though,
It tricked you?
at the first part.
What is the average access time for 100 memory references if you measure that 90% of the access to hits, 80% of the access to main memory are hits? So that
Just
means
with the first part, but then I thought about it and I was like, oh, because it was like 90% of the cache accesses are hit. So I was like, what about the other stuff? And I was like, oh.
yeah, it goes down, right? Anyone got this?
I don't think I put that in right, 208.9.
208.9.
I don't put it right.
Well, yeah, it's 0.9, so 208.9. That sounds about right. Let me do, because, yeah, 0.02 times 10,000, that's what, 200?
Yeah.
0.08 times 100 is 8, and then 0.9 is the cache access time. So which of these is the dominating factor?
Disk.
Disk. Even though the disk accounted for the least, or the fewest number, I should say, fewest number of accesses, it dominated the rest of it. So what does that mean? Don't ever go to disk. So you really want to avoid going to disk as much as you can. So some numbers, i7 4th gen. Oh wow, I haven't done updated this for the PS4. L1's 4 cycles, L2's 10, L3 40 to 300. Main memory is about 540 cycles. It really depends on many factors. PS3, it took 4,000 cycles to go to main memory. So what does this mean? What does this mean to you? Hmm?
Code to cache.
Cache. Code for everything to cache, right. You want everything to be in the cache. Otherwise, you're going to be spending a lot of time doing nothing. And then your game takes forever to load, and yeah, people aren't happy. Or your app just, or your PC program takes forever.
PlayStation, PS3.
Yeah, this is just PS3. PS4, I think, is a little better about this. The i7, these numbers haven't changed that much for the latest generation. The only difference is, the cycle numbers haven't changed much. The difference is your size of your cache has increased a little. Okay. So what is going on? Well, keep in mind the cache is keeping a copy of what's out in memory. So it's representing a small portion of main memory. And so it needs to keep track of which portion of that main memory it's actually holding. So you have two parts, the tag, which holds the memory address of the cache, or your cache block that you're working with, or the piece cache, and the block, which actually holds the memory data. So it's holding the memory address that it's referencing and the data itself. So compare the reference address with the tag. If they match, get the data from the block. If they don't, you have to go on to main memory. Quick organization. Cache memory consists of multiple tags or blocks. Obviously, you're going to have more than one piece of memory inside your cache. And when you put them in a pair, it's called a cache line. That's the tag and the block. We call it a line, cache line. If there's a tag match, that means it's in the cache. So that was a cache hit. If it wasn't in the cache, it's called a cache miss. Our goal is to keep the data we think will be accessed in the near future in the cache. That is the purpose of cache designs. Every cache miss will get the data allocated from memory, or get the data from memory, because you still got to go to memory. When it comes back, the cache will allocate that memory inside of itself. And then which should be allocated? Random. Well, which should be initially allocated? We could do random. Matt, you said random, right?
Mm-hmm.
But how am I going to grade your test if you do random?
Randomly.
Oh, okay. I'll keep that in mind. So am I feeling 36 today or 75? I don't know.
Random, yeah.
How can we
Plus
do
100.
plus 100? All right. How do we find the most likely address? Well, what's the probability of accessing a random location? It's just like accessing any other information. So pretty much random is not a good idea, especially since most programs are not random. They tend to use the same memory location over and over again. So really, if whatever has been the most recently accessed item will probably be accessed again. And that's what we call temporal locality. If you access a memory location like 1,000, you're more likely to re-access that location than some other random location. So if it was just accessed, go ahead and keep it inside memory or in your cache. All right, how does the cache do that? It says any cache data should be placed in the cache at the most recent location. That's right. It then basically states that the least recently referenced, this is what we call LRU, should be evicted to make room for a new one. So because the re-access probability falls over time as the cache line isn't referenced, the LRU line is the least likely to be referenced. So most of the time we consider LRU as the best replacement policy, most of the time. Let's do an example.
Now it just works like a TLB kind of
Yeah, it
thing.
is. A TLB is a cache.
Okay. Wow. I jumped to the end there, didn't I?
Yeah, you sure did. That was like, that's about 50 slides down. So good job. No, that's good. That's good. So let's do an example. Very simple memory system. Over here in processor, you have a bunch of loads coming out. Just to keep our lives easy, our memory has only 16 data values, just to be easy. Our cache can hold 2 of them. There's a tag and a data. And we have 4 registers. So first off, we're going to load from memory 1. That's the 100. Oh, I'm sorry. Let me look at the cache lines. In your cache lines, you have a valid bit that states whether this cache line is valid or not. There can be many, initially it's not going to be valid. So we need to have some trick to know if the cache is valid or not valid. That's why the bit is. So initializing, it's not valid. Caches aren't valid to begin with. We're going to load from memory 1. Is it in the cache?
Sure is. Not.
Not. Sure it isn't. In the cache, no valid tags. This is a cache miss. So we're going to allocate with the tag and then memory. So we put the tag right there, memory 1, because that's its memory location. Should we pull in the 100? Now it's valid, and then we send it over to the register.
Spiffy.
Spiffy. All right, we're good. Now we're going to load from LRU saying, yeah, that's the least recently used. Memory 5, is it in the cache? Nope. So it's another miss. Allocate it from main memory. That's valid. And then which one's LRU now? The top one. Because we just accessed the bottom. Now we're going to access 1. Is it a hit? Well, okay, I put it up there. This one's a hit. It's in the cache. So notice that we directly take it from the cache. We don't access main memory, so this is an example of how it would have been a lot faster. LRU's at the bottom. All right, how about 7? Come on, guys. Loud and proud.
No.
No. All right. It's a miss. Who is going to be evicted? The top one? Why do you say the top one?
It's already been
It's the, well, that's the most recently used. Or we do LRU is the least recently used. So I see where you're going. You just got backwards. Because remember, previously 1 was just used. So he's no longer LRU. It's now the 5 is the least recently used.
used.
So 5 is going to be evicted here. Pull in that value. And then write over to register 3. And of course, I have another read on 7. So we're going to call that a hit. All right. You get the basic idea? Great. Okay. So average latency is, let's see, cache latency hit rate plus memory latency hit rate. Why are we, yeah, times hit rate and the memory latency, that's correct. So 1 cycle plus 15, that's right, 9.4 cycles. In other words,
Miss rates for the cache. Yeah.
yes, miss rate of the L1 cache, you got it. So if we want to improve average latency, improve memory access latency, improve cache accesses, or improve the cache hit rate, because if we could have that 2/5 be higher, maybe 4/5, then we'd have a better average latency of our memory accesses. Okay, you can use this if you want to visualize it. Okay. Oh, another class problem. For application X running on MIPS 32, you measure 40% of accesses or memory, you measure 90% of the memory references hit the cache. Whenever a cache miss occurs, the processor stalled for 20 cycles to transfer the block from memory into cache. So that instruction takes 21. So what's the CPI? Oh, there we go. Great. I like this one. CPI, cycles per instruction. So we're first off assuming, we'll get you started, that 60% are not accessing memory, and we'll just say for the sake of argument they take 1 cycle. So there you go. 0.60 times 1. All right, so that's the first one. Great. What's next?
21 times 0.4 for the second one.
21 times 24.
0.4.
0.4. Where are you getting the 0.4 from?
The 40% to access the memory.
Okay.
Oh wait, that says for the cache though. Never mind. How many cycles does it take if it's just going?
It would take 2 cycles because you have to load it and then get it into your register.
Without the cache, or?
No, if it hits the cache. You also measure 90% of memory references hit the cache, so when a cache miss occurs, it's stalled 20 cycles. Oh, okay. When you, in your in-order pipeline, did load word stall your processor?
Yeah.
It did. So we'll say it stalls it for 1 cycle if it's in the cache.
Okay.
So that takes 2 cycles in total. So what percentage takes 2 cycles?
Uh, 0.4 times 0.1.
That's 0.9.
90% of the main memory references hits the cache, so it's 90% of 40%.
Oh, are you asking for the ones that? I thought you were asking about the ones that missed.
Oh no, well, okay, the ones that missed.
Yeah.
No, that makes sense, because you said that right. What was the ones you missed? You said
0.1 times the 0.4.
0.1 times 0.4, okay,
Yeah. Times
Okay.
the 20.
which is 0.04, 0.04 times 21.
But how are we going to calculate the other one eventually without knowing how long the it takes to load from memory?
Well, we're just saying that if it goes to memory, it takes 21 cycles.
Okay.
That's what this one says. This one's 0.04, but 21 cycles. So what's left is the 0.36. How long does that take? I think we agreed on 2.
Sure.
Sure. Okay. So what does that come out to?
A number. 1 point something. Maybe.
I think that's what I remember it being. 2.16. That's actually pretty good. Notice we got 90% in that first cache. All right. Application, what would be the CPI if there was no cache? Ooh.
0.6 times 1 plus 0.4 times 21.
And what is that?
0.84 plus 0.6. Oh no, that's a 21. I keep thinking that's a different number.
If there's no cache, then you're not gonna have a 1 cycle read. So that's gonna be, you said memory was 2 cycles?
Mm-hmm. Well, but you stall your processor for 20. So, what does that come out to?
9.
I think I came out with 9 as well. Just trying to show you the importance of a cache. Significant performance difference. Many factors. You see where I'm going with this, Bart?
Yeah, but I don't understand why you still got this 0.6 times 1 in there.
The
Oh.
0.6 is for ones that don't use memory at
Yeah,
all.
only 40% access memory. The other 60%, aka 0.6, are regular instructions. And we're just going to say, for the sake of argument, they take 1 cycle. Yeah, yeah.
Uh-huh.
The point of this is to show you that even if 40% of your references are memory, it still dominates what's going on. Even when your memory happens to be really fast, 20 cycles, our main memories that you've been looking at are hundreds of cycles. So this problem would be even worse. Yes, Matt?
I just love caches.
I know you do. Okay, how much does a cache cost? Cache cost? 2 bytes of SRAM, calculate overheads, probably another 4 bits. Yeah. So this goes back to our example. Let me go back and try and explain this a little better. These memories, the memory over here were each 1 byte, and you had 0 to 16. So how much is taken up in this cache line? That's the question. Well, obviously you need to take up a byte as well. So that's 8 bits right here for this block. How many bits is the tag?
The bits.
3.
Close.
2.
You're going the wrong way.
4.
Why is it 4 bits, Matt?
Oh.
0 to 15, that's
I was looking over there and saw it only went up to 7.
so 0 to 16 to 15, that's 16, which you need 4 bits in order to represent. Y'all following with that?
Mhm.
All right. Plus the extra valid bit. So 8 plus 4 plus 1 is 13. So this one takes 13 bits. Let's see. If it's a 32-bit cache, let's see what's going on here. So if your tag needs to it's a 32-bit machine, so instead of accessing 16 bytes, it's going to access 2 to 32nd bytes of information. How big is your cache line now? We'll still say it's just doing a byte, so it's 8 bits right here. But how big does your cache need to be, or your tag need to be, for a 32-bit system?
8.
Well, if you need to be able to access 0 to 2 to 32, how many bits do you need?
5.
Oh no, you would still need 32, is what I'm saying. Because to access all that address, remember, if you install 4 gigs of RAM, which is about 2 to 32, you need 32 bits to be able to reference every byte. So then it would be 8 bits plus 32 bits plus the 1 bit. And what is that?
41.
41 bits to store 1 byte. Well, that's just to tell you how much it cost. Oops. So how do we reduce the overhead? Well, we can have a smaller address. This is impractical because we want to be able to have as much RAM as possible, and caches are supposed to be non-architectural, so that's not going to happen. Cache bigger units than bytes. This is the first thing you can do. Each block has a single tag, and the blocks can be whatever size you choose. Notice beforehand our block was 1 byte. Well, we could have the blocks be about 2 bytes, 4 bytes. In actuality, I think it's normally 128 bytes, and that helps with the tag. Let's give you a little picture about this, about how this helps, and we'll bring in using our old system again. So this time we have 2 cache lines. This right here I'm pointing to is a cache line. That's another cache line. Each cache line has 2 blocks, or 2 bytes that it can store, and then a tag. So let's go ahead and do, this is a little different system, but let's go see how this one works out. Again, when you begin, valids are off because you initially start off as invalid. Is memory reference to 1, is that a hit or a miss?
Miss.
Miss, all right. Now, this was a little tricky. What data do we bring in? Well, the tag is just the beginning of that memory reference. Now, the memory reference is from 0 to 15, so its actual memory reference in bit format is 0001, right? Because you're accessing 1. So the tag is going to be the first 3 bits. Your offset's a bit, so the offset's going to tell you it's a 1, so it's going to go to the second block. Thereby, when you cache this, you're actually caching 2 bytes from memory. Now, you may think that this would slow down your memory accesses, but in actuality it doesn't, because main memory usually have a very wide bus and can give you the 2 bytes and actually can give you many bytes at once. It's the latency that's the problem. So this, oh, did you say?
I was just making the latency.
Latency, yeah. Bleh. So this is actually fine. It's just not really going to give us a performance problem, and also hopefully it gives us something else that we can use later. Okay. You understand the block offset now? All right, 5. Is it in the cache?
Sure isn't.
Sure is. So again, block offset. Ooh, that arrow's a little off. That's okay. The arrow should be going down here.
It's still technically right.
Maybe. LRU is up on top. Now the next one is a hit because it matched the tag. Notice the tag matched and then it just jumped over to the correct location of the block offset. LRU is down at the bottom now. Notice we're going to do 4. Again, it hits. Even though you haven't read in 4 before, or you didn't do a memory reference to location 4, it's still a hit because it got pulled in with the entire cache line. And then 0 again has a hit. All right. Did y'all follow that? Do I need to go over that slowly, or we good?
Yeah.
All right, great. Notice when we accessed address 1, we also brought in address 0. This turns out to be a very good thing since we later reference address 0 in this example. This was not necessarily a contrived example. It's actually very common for when you bring in one piece of memory, you're probably going to be accessing the memory close to it in the near future. This is something called spatial locality, where it says if we reference a memory location, aka 1000, we're more likely to reference a location near it, aka 1001, than some random location. So this is actually a very good technique for many reasons. One is spatial locality, the other is to save on the tag. All right. So basic cache organization, we have to decide on the block size. How do we figure out what the best block size here is? Let me go back and make sure I'm explaining that. 6. So over here, the block size was 2. It could have been 1. It could have been 4. But in this example, it's a little hard to take it out. Keep in mind, you might have 4 billion bytes, in a 32-bit system. So how many blocks should you have? Should you have 1, 2, 4, 8, 16, 32, 128? How do you think we just determine what the best block size is?
Roll the dice.
Roll the dice. I like that.
Trial and error.
Trial and error. You got it. No, you got it. No, you nailed it. You nailed it. That's exactly what we do. We simulate a lot of different block sizes and see which one gives us the best performance. That is exactly what we do. Most systems use block size between 32 bytes and 128 bytes. It depends on a lot of other factors about which one of those is the best, but for your particular cache, but that's generally what it is. Longer sizes reduces the overhead by trying to compare with the cam, namely with the tag, and also reduces the size of the cam or the tag. All right. Oh, good. Ooh, class problem. All right, guys. What's the cache hit rate with the following code is executed?
So I missed on the first one.
All right, so that's a miss.
I did my part.
Well, there's 3 of you and 5.
So you have to load. See, we're still doing
It should be a hit on the second one,
two
shouldn't
memory
it?
locations.
Yeah, so that one's going to be a hit.
Alright, I did my
that's a
part.
miss.
So what about the 9? Is that a hit or a miss?
Miss.
Miss.
Seems a hit.
Oh, tricky.
No, this one's going to be a miss.
Oh, yes, miss.
That one's going to be a miss.
11's a hit though.
And 11's going to be a hit. That's correct. All right. All right, good job. What about stores? Okay, let me go pause the video so it doesn't become this long discussion about caching.